And without further ado, I just want to introduce you our speaker today, which I'm super excited to have. It is Dr. Christopher Lucas. He is an assistant professor at the Department of Political Science at Washington University at St. Louis. He studies methodology, political communication, and media. And his ongoing work, supported by the National Science Foundation, develops and applies computational models for the statistical analysis of speech audio. Today, he's going to present his project, More Than Words, How Political Rhetoric Shapes Voters' Effect and Evaluation. And Christopher, the floor is yours. You can share your screen now.
Great. Thanks for that introduction, Olga. Let me pull up my slides. Wonderful. And everyone can see? It's all good? Great. So yes, thank you for having me. It's great to be here. One of the few positive things I feel like to come from COVID is sort of the increase in these sort of transatlantic type academic interactions. And so it's wonderful to be able to join and to do so without having to jump on a flight. So this morning, or I guess this afternoon, for you, I'm going to do the following. I'm going to try to convince you that the study of political campaigns presently misses an enormous amount of what's actually very important information about the way that candidates try to persuade and sort of win over voters and listeners. So this is joint work with Taylor Damon, who's an incredibly talented graduate student at Washington University, and Dean Knox, my collaborator at Penn. So every other study of political campaigns focuses entirely on the text of speech, that is to say, what people say, the actual words. And I'm going to try to convince you, as I was mentioning, that by focusing strictly on the text and by implication then ignoring these non-textual features, we miss much of what makes successful political campaigns and successful candidates ultimately successful. So importantly, I'm going to suggest that this isn't an omission that results from some sort of, say, theoretically informed position. It's not the case that on the basis of tremendous amounts of linguistic research, everyone thinks that all that matters is the actual words you say. But rather, my claim is that you and I both know that the way a candidate says something, how they say it, the way that a statement is delivered when they communicate to voters, that this matters, but that we ignore it as a field strictly due to methodological limitations. So this is a sort of omission not by theoretical justification, but sort of an omission due to just a lack of the right sort of toolkit. So in this presentation, I'm going to demonstrate why the sound of speech warrants academic study, and then I'll demonstrate a novel approach to studying its effects. So if you find all this hard to believe, I'm going to begin with a simple illustration. Now, I'm going to show you a short clip of former President Barack Obama. And as you listen, pay close attention to the effect of the speech on your impression of the speaker. So without further ado, President Obama.
You know what? That's not who we are. That's not what this country's about. As Americans, we believe we are endowed by our Creator with certain inalienable rights.
Now, Obama, as you're all undoubtedly aware, is an incredibly talented speaker. Imagine instead of former President Obama giving that speech, imagine that I was reading that same text back to you, that I delivered that same segment of text. Well, students in my undergraduate course would quickly corroborate that I'm nowhere near as engaging as President Obama, right? You'd be not even remotely as sort of positively affected, even though we'd be in this kind of thought experiment holding fixed the text of speech, right? I'd be saying the same words, taking the same policy position, and so on. But the fact that President Obama was reading it, right, mattered compared to, again, me reading it. Now, again, the strange thing is that all seems kind of obvious, right? Like we all sort of immediately expect a former president to be a better public speaker than an academic. And we expect that partly that was sort of why a certain subset of candidates or plausible candidates succeeded, why they were selected, that was something that they trained, that they learned to do, right? But if that's implicitly so obvious to all of us, why isn't that reflected at all in our study of politics? So with this example in mind, I'm going to attempt to convince you again more generally now that these sort of voter perceptions are affected by non-textual speech cues. But how do we do this? So in the remainder of this talk, I'm going to begin with a brief discussion of how we might study the text and the audio speeches. So this is going to build on recent work that appeared in the APSR earlier this year. Then to demonstrate the face validity of some of these claims, we built a novel corpus of videos which demonstrates that candidates vary their speech in a sophisticated manner, in a way that's consistent with the general idea that I put forward. We then conduct 2 experiments. So in the first, we show that candidates vary their speech, and that when they do, it leaves different impressions on voters, even holding constant the text of speech. And then we also, to do so, introduce a new method for approximate string matching, which we're going to use to construct an experiment. And then we conclude with a second experiment that probes the mechanisms of these different vocal styles, how they affect people. And in the second experiment, we hire professional actors to basically hold fixed precisely the text of speech and then vary things in a way that we couldn't kind of naturalistically vary in the first experiment. And in the second experiment, we conduct a conjoint experiment where we manipulate speech, again, with a combination of actors and computational manipulations. So how do we do this? So first, before I get to the experiments, I'm going to try to answer this question: why does this delivery matter? So what is it that makes speech effective? Effective speech, right, does a lot of things. It might establish credibility in the eyes of the listener. Someone might be perceived as wise, moral, strong, inspirational based on the way that they talk. They can appeal to the listener's emotion, right? So again, if you imagine reading the script of some really important scene in some movie that you really like, right, versus listening to it delivered by someone who won an Oscar, of course, again, those things have different emotive appeals. And they might be able to induce feelings like anger, fear, hope, and pride, all of which we know, for instance, increasingly that these things connect to and link to outcomes that we care about in politics. They might, again, try to, in parallel to these sorts of emotive appeals, use sort of logical reasoning to advance an argument, and that might be primarily in the text. So it's not our claim, of course, that the text doesn't matter, but it's that these 2 things matter in conjunction with each other. Now, recent evidence might suggest that this doesn't really seem to be the way the politics is playing out, but it's a possibility, of course. And again, as I keep trying to emphasize, we've known this for quite a long time, right? So even if we go back to, the stuff that your political theory colleagues read, Aristotle would talk about, the importance of rhetoric and of persuasion, and did so talking about the personal character of the speaker, putting the audience in a certain frame of mind, and then thirdly, on the sort of words of speech itself. So again, even back to Aristotle, there was writing on the sort of importance of these non-textual components of speech. And so we're going to use as outcomes that, again, we've cared about for quite a long time. So we're going to take outcomes from the ANES, and we're going to study, so the ANES has for decades asked about whether or not a candidate makes the respondent feel angry, proud, hopeful, if they're strong and moral, etc. And so again, firstly, this illustrates that we do care about these sort of outcomes, and we've cared about them for quite a long time. And we're going to link that again to this missed component of speech. So where is that persuasion in speech? Where would we find this? Just empirically, where does this exist in the data? So imagine now that we took that brief clip of former President Obama from a few slides ago, and we tried to analyze it with sort of standard text as data approaches. Well, all of a sudden, your data you'd probably process that as a term document matrix, and suddenly your data looks like this, right? It's just going to be the frequency of different terms in the text. Importantly, again, imagine in that experiment where I read it and former President Obama did, we would get the same representation in the text, right? Like this data would, again, not differentiate that I said it versus President Obama, and the effectiveness in the sort of way that he's going to deliver that speech relative to mine. So I'm going to suggest that it's not necessarily, at least entirely, in this term document matrix. So where else would it be? So this is the loudness of speech over that same clip. So along the horizontal axis, we have time. Along the vertical axis, we have just the volume, right? So this is a simple intuitive measure. Now, we can plot over that the words, right? So we might see that by using the volume of speech, the president was emphasizing certain terms like certain, inalienable. That's not, right? So not gets quite a lot of emphasis there. Pauses after key phrases and so on. Similarly, instead of loudness, we might consider the, say, pitch of the speech. So this is now the pitch instead of the volume. So again, sort of from low to high, right? And so again, on the horizontal axis, we still have time, but now vertically we're representing the pitch. So higher represents a higher pitch. And then we've removed parts of the speech where pitch can't really be estimated. And so we can see similar sort of emphasis on different words, right? Like emphasis on nationality, so as Americans, going up in pitch there, and so on. And so we can put that all together to get a fuller sense of how a candidate might communicate with voters. So in that actual clip, right, we end up saying here we're letting color denote the loudness, you know what? And then again, the horizontal axis is our pitch. That's not who we are. That's not what this country is about. Theatrical pause. As Americans, we believe that we are endowed by our Creator with certain inalienable rights. Right? Now, again, proof of concept. I'm clearly not as good at saying that as President Obama did, but you get the general idea. So, how would we go about actually looking at sort of actual, real, kind of observational campaign data, thinking about speech in this way? So we know that sort of anecdotally, there's all sorts of evidence, again, that candidates are assessed this way. So for instance, Hillary Clinton was criticized as being too high-pitched and in order to be likable, earned the nickname Shrillery at some point in the campaign. And so we want to look at this sort of less anecdotally. So we created an original corpus of campaign speech data. So we collected 100 videos from the 2012 presidential race. We cut this to single speaker speech. This is about 30 hours. So we dropped, the person introducing the speaker and so on. And then we're going to quantify vocal delivery with two features. So we focus on patterns in loudness and pitch, both their mean and their variance. And then we pair this text with the with text that we extract from the Google Speech API. So on average, that means we've got about 20 minutes and about 3,000 words each. And then we're going to also use dictionary classification, to classify the issue area. And so I'll say more about that in a bit. But so in short, this is our data structure. So for each speech, we have a transcript, we have a location, we have a date, and we have a speaker. So let's begin with a high-level analysis of the two candidates in the election and their sort of speech style. So in these two panels, we're plotting the loudness mean and the loudness variation. We can add pitch. And again, we observe a simple trend that basically Obama seems to modulate more. So again, modulating here is just the variance in that feature. Whereas again, the mean is strictly the mean. So Obama seems to basically vary his speech more, to modulate more, to not be as monotone as Obama. This sort of makes intuitive sense because again, we sort of have some general kind of impression that Obama's a more successful public speaker than Romney. And then we can also look at issues to look at how maybe certain issues are talked about differently, right? Not just in terms of text, but about the way that the speech about it is delivered. So here, we're going to break down President Obama's speech according to issue using the Lexicode Policy Agendas Dictionary. So with two affix effects for speech and topic, note that there's some clear issue-related variation in delivery. So I'm going to highlight a few examples that are significant after multiple testing correction, and we can pull those out. So the red estimates are significant after a multiple testing correction. So let's zoom in. So we can look at education, and on education, we note that President Obama seems to speak at lower volumes, but to modulate more, for instance. So
we shouldn't be ending college tax credits to pay for millionaires' tax cuts. We should be making college more affordable for everyone who...
Sorry, I said lower volumes, but clearly I meant higher volumes. So Obama speaks at higher volumes, modulates his pitch more. So the the modulation and both loudness and pitch is higher. In contrast, when discussing religion, we see lower average pitch, but again, more modulation on average. So something consistent with a kind of reverence that someone might emphasize.
And you and I together will remind the world why the United States of America is the greatest nation on earth. God bless you. And God bless the United States of America.
So why would a candidate do this? Why vary speech in this way? So we're going to suggest that voters or the candidates vary their speech in this way in order to generate support and form impressions with voters that are going to be beneficial in some way when they're evaluated at the ballot box, basically. So how do we assess this? So we conduct 2 experiments, as I mentioned. So as a thought experiment, of course, what would our ideal experiment look like? Well, ideally, we'd call up, President Obama, Romney, and so on, and have them sort of participate in our study, maybe record some examples, try to be convincing versus not. They didn't respond to our emails. So we did the next best thing, and we conduct 2 experiments, one again with these sort of naturalistic treatments that we create. So I'm first going to talk about that. Again, ideally, we'd work with the candidate on a bunch of different messaging tests. We'd expose small groups to some random message, but because we can't do that, we do the next best thing, which is we try to find catchphrases in our corpus, where a catchphrase is basically a piece of text where they say the same thing over and over again at different rallies, but where across those different instances of that catchphrase, they're going to vary how they delivered it. So they're going to, in one case, maybe say it sort of softly and with a kind of calm demeanor. In another case, maybe emphatically. And that might be due to the way they felt that day, if they had their coffee, or just sort of the demeanor of the room, if it's a small group versus in a large rally, and so on. So how do we do that? How do we discover catchphrase? So we'll take a brief detour now to talk about an approximate string matching method that we developed in the course of this project. So in order to conduct the experiment, we need to find paired text that is similar but not exactly so. Because again, if we look for exact matches, we would just find very few due to small differences in text. So it turns out that this was an incredibly computationally intensive problem. And so to see why, imagine for a moment that this red piece of text is the catchphrase we want to find in the rest of the corpus. The problem is that the number of possible matches is basically any string of approximately that length, right? And of course, there are very many of those. Even in a small corpus, that becomes very large, because again, not only do we don't ex ante know the strings we want to find matches for, so we want to find all possible repeated catchphrases without ex ante knowing what those catchphrases are. So we want to look in the entire corpus for every single possible catchphrase, right? Where again, imagine just for the sake of simplicity that a catchphrase is any string of length 5 or 6 or 10, right? So the possible strings of length 10 becomes, it's what, the number of words in the document minus 9 or something, right? Because you can just increment forward every time. And then the number of matches again becomes equal to the number of, basically that same number in every other document too. So this becomes really big and exponentially so very quickly. So what do we do? Again, in a traditional algorithm, we take this red text, we'd look for the blue text as a possible match. We compare these, increment forward, and so on and so on and so on through the whole thing. And then we'd increment forward to every other possible catchphrase and look at every other possible match and decide what the match is. Now, the problem, as I was mentioning, is that traditional methods are too slow. Basically, we just can't calculate string distance that many times in a way that was remotely suitable for the scale of finishing this project before tenure. So to do so, we define a new similarity metric between k-word sequences. So imagine where again, k is just the length of the catchphrase, so the number of terms in the string. So let P be Q, be K by L word letter matrices, where basically P you can think of as a needle and Q is a substring of the haystack. So we're looking for a needle, the possible catchphrase, and a haystack, the corpus. Q is a substring within that haystack that might be a match for the needle. And then L, of course, is 26 because we're using English and there are 26 letters. So an example, here's one particular needle, a catchphrase we might look for. We've doubled the amount of renewable energy that we can generate, or that we generate. The associated matrix with this is the following. So on the x-axis, we have just letters. On the y-axis, we have the words, and then the entries are just the number of occurrences of that term. So what we've basically done, right, is turned that string into this, again, instead of it being a term document matrix, right, you can think about it as it's just a word letter matrix. And so what we're going to then do is define a measure of similarity that's basically just correlation, but in multiple dimensions. So this is going to be the similarity between P and Q, which will compute via a Fourier transform, which will make things fast. As with correlation, it will be bounded -1 to 1. In a one-dimensional case, it would just be correlation. So to demonstrate this algorithm, here's the text of a specific haystack. So this is a quote from a rally in Madison, Wisconsin, I believe. To the right, I'm going to display the haystack's representation in word letter form. So that's this blue matrix. So this is the haystack in which we're going to look for matches for our needle. Our red matrix, again, is the needle that we're looking for. So the way this works is we compute the similarity in this first starting position. We increment forward, we compute it again. And on this far vertical on the right, I'm going to basically represent the similarity hypothetically in this comparison. So the similarity is incremented forward, increased, or our score of similarity did. We can increment again. Oops. Oh, I messed up. You got to see the whole thing. Okay. We increment again, and we can do this for the whole corpus and get similarity at each point. And then we declare that this is some match because it is above some thresholded level at which we declare a match sufficiently good. And of course, we could vary that and so on. So the intuition as to why this is fast, there are several reasons. One is just that because we can do this with Fourier transform, it gets quick. But another is that basically, as we increment, we can reuse the what we knew from the previous calculation of similarity at, say, start position I. And when we increment to I+1, we know a lot already about similarity because we had all but one similar, we only incremented once, right, in that position. And so all the other parts of that matrix are still in there. And so we basically don't have to redo all that computation. So as a result of this, again, we would find a match, like, say, the blue string for the needle, which is the red string, and a haystack, which is, say, the paragraph here. So now we can identify similar phrases within the corpus and do so efficiently. So we use this method to find plausible pairs of text within the corpus, and then we take 30 pairs, varying delivery, and show these in the experiment. So respondents see either text, audio, or video, and they see two statements, again, holding fixed the text, or holding approximately fixed the text. And then they're told, seeing both these pairs, or both instances of this catchphrase in this pair, they're told to pick which one is more consistent with the leader who is, and then the dimensions from that ANES survey that I showed you. So which is makes you angrier, or which makes you, and so of course the subjects assigned to the text condition were often, they were just randomly picking, right, because the text was mostly held constant. Now I will note it was the case, and so this is one of the reasons we did a second experiment, but sometimes these approximate matches actually were different in a way that mattered. So in this example, you'll note that in one rally, this is a quote by Obama, in one rally, President Obama said, no company should have to look for workers in China because they couldn't find any of the right skills in the US. Actually, I think this was wrong. And then in B, no company should have to look for a worker someplace else because they couldn't find the skills here in the United States. Now, our string alignment algorithm, I think rightly, right, found that these were similar catchphrases, but our survey respondents in the text condition would pick up on these really subtle differences sometimes. So depending on the actual text, there were either, it looked like a coin flip, or really small differences like this would affect outcomes. If they were assigned instead to the audio or the video, again, they listened to it or watched it. So for each pair, 350 respondents selected the recording that was higher on 8 dimensions. These are verified voters in the 2012 election. Which one makes you feel angry, hopeful, proud, is more consistent with a strong, moral, inspiring leader? So here are the results. So first, I'm going to show you the results for text. So what I have now, each panel in this plot represents one catchphrase, one pair of text. The black dots are just the proportion of respondents indicating that A of the first of the 2 examples in that pair is more consistent with or makes you feel any of the 8 outcomes that we measure. So strong, proud, moral, afraid, angry, etc. You'll note that some of these, like the offshore example, which was, I'll show you in a second, but the offshore example, of course, we actually got big differences in text because of small differences in the actual words in those 2 examples. Other cases are where the text didn't have these sort of subtle differences that actually ended up mattering quite a bit, like say the military case, him, etc., look consistent with just kind of coin flips. So we can zoom in, again, Medicare consistent with coin flip, but this offshore example and the opportunity example, again, we had strong preferences for one over the other over these different dimensions. And this one, the offshore example, is the one that was China versus someplace else. Now, what's important, and here's what the main takeaway is from this first experiment, is that when we show the text versus the audio, so the red dots now are the proportion selecting the audio as being, or selecting the first example as being higher on those 8 dimensions when shown the audio of the recording, we get very different sort of trends. So again, the offshore example starts to, it still matters a bit that they said China versus someplace else, but we start to see different results. The opportunity example basically flips. It's basically symmetric, as is the terror example and so on. And importantly, and interestingly, I think, when we show them the video, we get sort of similar results with the audio. So it doesn't appear mostly that, you know, so the work example is a great one. The text here is almost exactly the same. And we get, or it doesn't differ in any substantial way, but we get sizable differences between A and B in the audio and the video conditions. So again, military as well, another one, and so on. And so if we just looked at, if we try to look at whether or not there's a statistically significant difference between these conditions, if we pool all the different examples, it's significant and yeah, and quite large. But so the big takeaway here is, I'll show a couple examples here. So these are subtle differences. So I'll play that one more time. So these are very like small differences in delivery. So here's one pair.
Let's put Americans back to work doing the work that needs to be done.
Versus,
let's put Americans back to work doing the work that needs to be done.
That's a very, very subtle difference, right? Similarly, and this is the work condition. So that text, again, was sort of basically exactly the same. And despite that, we got relatively large, I think, large relative to the strength of that treatment effects on the responses from subjects.
We don't believe that anybody's entitled to success in this country, but we do believe in opportunity. We don't believe that anybody's entitled to success in this country, but we do believe in something called opportunity.
Now here, subjects, again, unsurprisingly, I think, had a sort of strong preference for one over the other. Here it sort of flips, the reason being that the transcript that we showed them in the text had that kind of stutter in it. And so when they, but apparently the quieter, more sort of subtle delivery mattered for when hearing it. So what I want the big takeaway again here to be is first, even with relatively subtle differences, voters seem to have or to form impressions differently based on delivery. But these are really subtle treatments. Obviously, we can't hold everything else fixed, right? We had all sorts of things varying, like you know, in the video condition where they were giving the speech. But we also want to kind of explore the range of delivery style in a a broad way, and do so in a way that lets us kind of probe mechanisms. So in experiment 2, we're going to probe these mechanisms with voice editing and actors. So we're going to work with actors to create a bunch of different recordings of catchphrases from this corpus. And then we're going to also we're going to have them introduce sort of variation in how they deliver the speech. And we're also going to manually vary some other dimensions too. So what do we do? As I mentioned, this is a conjoint, so we're going to factorially manipulate speech in the following ways. So we have 4 artificial manipulations. So these are ones that we do manually in sort of post-processing. So we manipulate the pitch and then the volume, basically, and into 2 categories: high, low, loud, soft. Here's one recording, no act of terror. I'll just play it for you.
No act of terror will dim the light of the values that we proudly shine on the rest of the world.
So that was one of our actors.
No act of terror will dim the light of the values that we proudly shine on the rest of the world.
That's our manual manipulation of volume.
No act of terror will dim the light of the values that we proudly shine on the rest of the world.
And our manual manipulation of pitch. We have 10 voice actors, half women and half men.
No act of terror.
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 No act of terror. No act of terror.
No act of terror. No act of terror will dim the light of the values that we proudly shine on the rest of the world.
And these 10 voice actors also manipulate the speech themselves. So they manipulate the speed at which the sort of rate of speech, which we couldn't manually manipulate in a way that sounded naturalistic. Once you speed something up manually, it, as you probably know, begins to sound strange. The pitch will go up, so you have to then manually lower that again, which sounds artificial. And then we also had them modulate both volume and pitch. So basically, there was a monotone condition and then a sort of more naturally varied condition. The actors really didn't like doing the monotone condition, so they felt like we were kind of asking them to deliver the speech badly. And so that was one of them sort of asked like 3 times if we actually wanted them to do this because they thought it would be less convincing, which again is a sort of further indication of people sort of knowing that these things matter. So again, in that big example, no act of terror.
And no act of violence will shake the resolve of the United States of America.
So,
and no act of violence will shake the resolve of the United States of America.
So that was our normal speed versus our slow condition. And then for our monotonous delivery.
And no act of violence will shake the resolve of the United States of America.
So again, these are still relatively subtle treatments, but they are there. And we had 6 different campaign scripts on various issues. So rather than just use a single script, which might interact with some of these treatments, we used a few, which are about nationalism, the budget deficit, and so on, from our corpus that we identified or discussed a bit ago. And so first, what I'm going to show you are baseline differences between speakers. So here I'm plotting the average evaluation on a feeling thermometer, basically, of these 6 outcomes, whether or not the leader sounded competent, enthusiastic, persuasive, trustworthy, and so on. The letters correspond to their names. So each of these are individual speakers, and then the colors are the speaker gender. And so first, from this plot, I want to highlight one thing, which is that just the across-person variation is substantial. And this is further evidence of the fact that these sorts of things matter, right? That delivery matters, because again, here, the candidates all are reading the same script. So we've held fixed the statements that they're making, and we still see broad, consistent patterns with some candidates being perceived as more trustworthy, more competent than others. So for instance, actor A, we didn't show them the results. I think it would have made actor A quite sad. Actor A, right, was evaluated as being relatively incompetent compared to the rest of the actors. Actor J was evaluated very well. And then we also asked them just general willingness, to vote for this candidate, which is the next slide. Yes. And on that general willingness to vote for the candidate, we saw, again, the same kind of general trend. So speaker A was again penalized across all these dimensions. People in general said they didn't really want to vote for them, compared to J, which there was quite a lot of excitement about. So again, that's also consistent with these different evaluations that on these different dimensions, the candidate that they said they were most willing to vote for was the one who was evaluated the best across competence, persuasiveness, trustworthiness, and so on. But what we actually really care about, though, again, are the effects of the manipulations that we talked about. So here are those. And so you'll note, right, that when subjects were assigned to the slower speech condition, in general, they were penalized effectively, or they penalized the speaker. So that is to say, faster speech, the faster speech condition was generally rewarded as being associated with higher levels of competence, general trustworthiness, persuasiveness, and so on. I will say, I think that that's mostly, obviously, these are not going to be perfectly linear effects. At some rate of speech, you'd get penalized. That is to say, in the limit, of course, if you're saying things instantaneously, that would not be very natural. And so, we've obviously just compared means at two levels. And I think mostly probably what's going on in the rate of speech thing is more that the deliberate kind of slower speech is actually perceived as oddly slow, rather than, oddly fast speech being rewarded. Similarly, there are large effects for modulated speech compared to sort of more monotone speech. So when the subject is assigned to the recordings of the modulated speaker, again, that's rated very highly across these 6 characteristics. And again, consistent with our previous results, we see the vote evaluation kind of aggregate these individual characteristics. So again, rate of speech and modulation were both positively affected the respondents' expressed willingness to vote for the candidate. So, and if we break that out by gender, we see sort of similar effects. It does appear that basically modulating more in general might help women more than men. I think partly that's because there's more of a penalty against women to begin with. I will say we wanted to, so when we did this experiment, we were interested in just general gender effects too. But with basically with just 10 actors, it's very hard to say too much about what's a gender bias and what's a sort of specific feature of those, say, so for instance, that one candidate or actor A, right, had a very negative set of responses compared to all other actors. So I think in order to say much with confidence on that, I think we'd like to do this with more speakers or maybe another corpus where we don't have to hire people. But it does appear, I think, in general, that there is, unsurprisingly, sort of gendered interactions with some of these treatments. So that's a thing that we didn't totally unpack here, but would be interesting to look at moving forward. And again, we see the same thing similarly in vote outcomes. Now, again, like I said, I think the modulation thing is partly because the baseline is lower for the female candidates rather than the benefit. So it's benefiting more, but sort of as a function of that lower baseline. So in summary, we've conducted what we believe to be the first descriptive analysis of campaign speech style. We've shown you descriptive results indicating that candidates do in fact manipulate speech in a way that's consistent with their belief that this is strategically beneficial. And then we've shown you experimental evidence that real world differences in speaking style have effects on real world voters, and that this vocal channel conveys information that's lost in text. Finally, in a second experiment, which I just showed you, we've unpacked the mechanisms a bit. So found some vocal channels which shape perceptions and compared them to sort of baseline levels of different ways of speaking. So again, I want to come back and conclude on this following observation that I think really what I'm trying to convince you of shouldn't be, I don't think, that difficult, right? We all sort of know that this matters. Pundits talk about this mattering. The way that people talk matters. We all are well aware. Anytime we sit in a job talk, often, right, if you have a student on the job market for the first time, They end up getting a ton of advice just on the way that they deliver the talk, right? The way they talk too fast. I at least got this criticism quite often, so I'm sure that, that others probably have too. And so we know this matters, right? It just isn't a thing that we've actually thought about very seriously when we think about studying candidates. So I'll conclude there, and there's more information about my collaborators at their respective websites as well.
Great, thank you so much, Christopher. So we have a couple of questions in the chat already that I presume I will read unless the speakers want to ask the questions themselves. Yeah, so the first question was from Ken Benoit. So how do you determine the optimal lengths of the needle for such searches? Yeah,
that's a good question. So we basically did it by varying the length of the needle, and then just picking the one that qualitatively seemed to give the sort of most interesting matches. So obviously, if the needle is length 2, then you get way too much of sort of uninteresting matches. The needle's length 30, you get basically 0. And so we set it at different levels between like 5 and 15, and then had people manually go through and basically discard the ones that weren't interesting. And then we went through and discarded them. And then we found all the actual recordings and tried to identify ones that basically qualitatively seemed like good pairs. So yeah, in this case, basically the way that we did it was just sort of manual validation.
Okay, cool, thank you. And another question from Sahil Jill. Do the evaluations also differ depending on the gender of the listener?
That's interesting. So we didn't actually look at that. We didn't break down this by we actually should do that. I don't know why we didn't do that. Yeah, they probably do. we didn't actually do that. So that's a good suggestion.
All right, another question in the chat from Umesh Rathod. How was ethnicity of the listeners considered in the experiment?
So we didn't vary, again, we didn't, for ethnicity, that was a conscious choice to not look at with respect to the listeners. And the reason was I think would have had to oversample in order to be powered to say something about different ethnic groups. So this was verified voters on Mechanical Turk. And so, as you probably know, most of those it's not representative on ideology in general or these background characteristics of the listeners, which is partly why we didn't make too much of those interactions. But I suspect that obviously that would matter, and particularly is the sort of thing that people talk about a lot when they think about these things mattering, right? So home style and such is sort of one of the kind of common ways that these sorts of strategies get discussed in popular media, I guess.
Okay, the next question from Felix Rouchet. Did you consider other outcomes using observational data, such as the loudness, length of applause, or the winners of TV duels, I guess, debates?
We didn't do that. We could. So we've in other work trained classifiers to identify applause, mostly actually as a pre-processing step to remove that from recordings. We could very easily just look at length of applause. Yeah, that's a good suggestion.
Another question from the chat from Alexandros Christos Gotinakos. Sorry if I'm mispronouncing. Where can we find more on this piece of work? So I guess maybe the question is like, where can be the paper found, or maybe some other related literature? So I don't know, something like that.
I have the paper. I think it's hosted on my website, but I don't think I linked it. Anyway, I can. If you shoot me an email, I'll send it to you. I was going to tweet about it at some point in the next week or two. So, but if you want it sooner than that, you're welcome to email me. I'm happy to send you a draft.
Okay, and another question in the chat from David Pressburger. Is there a structured data set for the recordings of speeches like the Parle debates database? And would it make sense to store the pitch, loudness, breaks, etc. within the text data, like putting the pitch in brackets behind the words?
Yeah, that's interesting. So we've thought about, so I think in text classification, we haven't done this, but we've thought about doing something that basically is like kind of horse racing features in terms of just like, and I think in general, it would be interesting with respect to certain outcomes if you were, say, in some supervised classification task. What I think is interesting about it potentially is that obviously the kind of importance of these features is going to vary with respect to the target. So like if we were trying to classify something related to sentiment, I think that these things probably are tremendously important. So some of the earliest work on you know, these sorts of features and audio classification is actually stuff related to applications to like helplines, where you might get some automated response and then they want to identify, is this person really mad? So we can send them to a real person. Point being, something like the anger of the speaker is very importantly conveyed through these channels. Conversely, though, something like topic, right, is probably much less dependent on these things. So if you were trying to determine the topic of speech in some classification task, presumably this is in most cases less interesting. So I think it would be interesting in general to include that jointly with the text to kind of think about what labels really benefit from this. So yeah, that's a good suggestion, something we thought about. With respect to the first question about a structured data set, we were working on, so we just got an NSF, part of which is going to be the construction of sort of like basically a database and different databases with this type of data and with examples for analyzing it. So we don't have a super clean thing posted yet, but that's something that we hope to get online in the next 6 to 12 months.
Awesome. So this is, I think that's all the questions in the chat, but maybe some of the participants want to, if you want to raise a hand and, you know, ask a question out loud, feel free to do that. Oh, there's another message. Oh no, that's just thanking for response, I guess. Okay. I guess no more questions in the chat. There's no hands raised. I don't see any. So maybe then I can ask a question while just abuse the power of the host. I guess I was wondering a bit more about maybe it's not part of this particular paper, but about the package that you mentioned in the beginning of your presentation. If you can tell more about that, because as far as I understand, that particular paper is more experimental, but you also have some more computational, you know, audio processing things. So that kind of would be, I'm just curious to hear more about that. I mean, I've seen the paper, but it would be nice to, you know more from you and your experience of applying to this type of like speech data.
Yeah. So we continue to do work on Ken's Quantita package is really the aspirational target of what we'd like to make. It's, you know, far from it, but you know, what we'd love to, the goal would be to make something similarly straightforward, but that is to say similarly easy to use, but that is for audio. Right now, much of the computational bottleneck, as probably your question surmises, is in just featureization, which is difficult, firstly, because of the size of the data often, and then the density of the features themselves. So unlike, you know, if you imagine something like a term document matrix for a single speech, right, that reduces to just the number of unique terms, right, and we can give that this vector representation. If we had that over a bunch of campaigns, right, again, we just have, you know, a number of unique terms by number of speeches. And so the size of that, first, is it's sparse, so there are lots of zeros, so that becomes easy to shrink on disk. But it also, the size of the data grows the rate of growth slows as we get more and more data, because basically the number of new columns that we have to add for every additional document goes down because the number of new terms goes down. So the vocabulary doesn't grow as much if we add more and more documents. So it obviously increments in the number of documents, but the columns increment slower and slower. So anyway, text data is big, but you might be, if you're working with a text corpus of 30 gigs, and a term document matrix, it's a gig or two, like that's crazy big, right? At least in my experience. With audio, a single recording might be half a gig or something like this, right? And then the features, because they're dense, and so they're often, I didn't talk about this, but in the APSR paper, we were doing supervised classification with audio. And so we calculate the features at every, we calculate them at every 12.5 milliseconds over a 25 millisecond window. So if you think about that, and then we calculate, depending on what you want, between something like 15 and 85-ish features. So that quickly becomes very big just on disk itself as well. Often approximately, depending on the quality of the audio, it can be approximately as big as the recording itself. So you can very quickly have like terabytes of data on disk. I'm working on another long-running project that is about it's order petabytes of data, which is not a thing that you really ever want to be engaged in. It really is sort of silly. And so that's a big challenge, is first just the size of everything on disk, the speed at which you can featurize, and the density, and ultimately size on disk of the features. So the package does all the feature extraction in C++. Now, it didn't in an initial version, but now it all does. That's not the version. Anyway, so it's an ongoing thing to speed that up. You still obviously, no amount of software package, effort makes the raw data smaller. But we have also tried to think about just doing things to make this work naturally and easily with various cloud computing things too. Yeah, firstly, that the feature extraction stuff is as fast basically as it can be in the beta testing version of the package. And then in the APSR, we develop a supervised model, which is a hierarchical hidden Markov model for classifying speech. And that also, in addition to classifying speech, it is sort of modeling the dynamics of speech, so interactions between people. So I think about the two projects, or the kind of different components of them as being, as you kind of rightly intuited, here we're kind of doing an experimental test of the effects of these sorts of things on listeners. In the case of developing the supervised model, we're firstly thinking about just labeling, right? So maybe the things that we're thinking, okay, if we vary these components of speech, how does that affect listener responses? And the other paper basically is the inverted part of that, right? Imagine that you had listener responses, kind of which types of recordings made someone angry, right? You can imagine trying to label that. And also, again, this element of speech dynamics too. Is that suitably, that was a long answer to your question, but.
No, that's super interesting. Yeah, I was kind of curious about this train part, like the labeling. What is the actual label? Is it exception or?
Yeah. So yeah, I mean, it could be whatever labels you want. Whether or not they're recoverable from the features is a separate empirical question, and a function of the labels. But in that case, in the APSR, we did basically what sounded like a skeptical question from Supreme Court justices, which is a relatively subtle category. It was a category that basically the text couldn't classify at all. If you tried to recover those labels with some text classifier, it was just garbage. It was basically randomly guessing. But you could do, again, I think a lot of probably what labels are going to be the most easily recoverable in audio features is going to be these sort of emotive things, right? So again, something like topic of speech is almost certainly not going to be recoverable strictly from the, and there might be some association, but it's not going to be as easily or as obviously recoverable than would, something about the emotion of the speakers, say.
Thank you all for being here. Thank you so much again to the speaker, the host, and everybody who asked questions. And we look forward to seeing you again sometime soon. Thanks and bye-bye.